Welcome to this course on manufacturing for turbines. So in this lesson 18 of this course, we will see the investment costing route for primary manufacturing of the steam turbine. So the outline of this lesson will be as follows, in which we will cover the investment costing process in detail. So we will look at the overview of the investment costing process. We will see what are the design for manufacturability or DFM considerations. We will understand various steps which are involved in investment costing process, and subsequently we will look at how investment costing process is used for steam turbines and conclude this lesson. So as we have seen in the previous lesson that steam turbines are one of the vital sources of generating energy from steam power, and steam power can be generated by either burning fossil fuels like coal or natural gas, or it can be generated by nuclear reaction, primarily nuclear fission reaction. And as we have also understood that to improve the efficiency of the steam turbine, the operating temperature as well as the pressure, it has to increase. And as we are aiming towards ultra supercritical steam turbines, so which have the operating efficiency of the order of 60%, it is very essential to understand what materials go into making these turbines. As we have discussed in the previous lesson, the various alloy steels, specifically containing chromium and nickel, are widely used to manufacture the steam turbines. And now we will see how the casting or the manufacturing processes are done for manufacturing the steam turbine. And in any manufacturing process, to start with, for any product, it is the primary manufacturing processes that come prior to the secondary processes. And in this, the casting process is one of the well-known primary manufacturing process for any component. So casting, as we know, it is a process in which we allow the molten material to solidify inside a cavity, inside a mold cavity, and upon solidification the material takes the shape of the mold cavity. And to create this cavity, we know that we utilize patterns, and patterns are basically replica of the product which has to be cast. Now casting processes are there in wide range, and again as we have seen in the beginning lessons of this course, how the selection of the manufacturing process is dependent on several parameters. So in this regard, the investment casting route, as we have seen earlier also, was a very popular route for the nickel based superalloys which were used to cast the gas turbine blades. The investment casting route is also popular with the steam turbines. So in the investment casting route, as we have seen earlier, that it primarily consists of the pattern which is made up of wax. So here the pattern material is wax, and this process is also known as the lost wax process. So in this process we have the die which is constructed. So inside the die we inject the wax, and upon solidification the wax will take the shape of the die. So these solidified wax patterns are then assembled onto a assemblage of this sort of a tree. Subsequently, this assembly of various wax patterns is dipped in a slurry coating and subsequently followed by a stucco coating. So purpose of this slurry and stucco coating is to achieve a desired shell thickness, and once the desired shell thickness is achieved, we will take this assembly of the wax pattern inside the slurry and stucco coating into a furnace, where the heat of the furnace will harden this ceramic shell, and at the same time the wax which is present inside will be melted out, and this wax can subsequently be recovered and reused to make the new patterns. So whatever is left behind is the hollow ceramic shell, and subsequently molten material is, or the material for in this example, in this case, is the nickel chromium alloy steel is then molten, is melted and poured into this hollow ceramic shells and is allowed to solidify. Upon completion of the solidification process, the shell is removed by breaking away this ceramic shell, and individual pieces or the components are cut from this assembly as shown here. Subsequently, some minor finishing operations may be needed, after which we can perform the inspection of the cast product using various non-destructive testing methods. For example, one of the methods shown here is using X-rays, which is a non-destructive testing method, and this can help to detect defects inside the material. Okay. So why investment casting is so popular with the even with the steam turbines? So as we know, investment casting is one of the preferred route in case we want to cast products with intricate geometries. So investment casting is very helpful to create complex shapes with tight tolerances, which is very ideal for blade design. Superior surface finish, because the pattern of wax it leaves behind a very smooth surface on the interior walls of the cavity, which helps to produce the smooth surfaces which help to further improve aesthetics as well as minimize friction and improve the efficiency of the product. Specifically with turbines, we are looking at the turbine blades which have aerodynamic considerations, and smooth surfaces are very much essential for aerodynamic efficiency. Then the investment casting process, as we know, is very versatile. It can allow casting for these high temperature melting nickel based superalloys as well as nickel chromium alloy steels. And thirdly, because the investment casting process is based on this wax pattern, it is very easy to create patterns in complex shapes. So whatever product is cast from the investment casting process, it is utilized in the near net shape. So near net shape means it reduces the need for extensive machining, as well as it also saves time and material. So this is the overall methodology of the investment casting process, which starts with design and pattern creation. Then is the wax injection process. Then is the assembly. Then is the ceramic shell building, dewaxing, metal melting and pouring, shakeout and cleaning, and lastly is the finishing and inspection. So now if we look at the design for manufacturability considerations in investment casting of these products such as the steam turbine blades. So first we will understand what is DFM. So DFM is a philosophy which focuses on ease of manufacturing, which improves product quality and productivity of the process. So for every process or every product, there are certain points specific to that product in which the DFM philosophy can be applied. So the various points which are considered under DFM for such casting include design of component with efficient wax pattern removal and mold filling. So whatever the design of the pattern has to be done, it has to be done keeping in mind that we efficiently utilize the wax for the mold filling. Secondly, we also help to minimize the sharp corners and internal features to prevent cracking during casting. Because this presence of sharp corners and internal features, generally they become the point of stress concentration, and upon solidification there may be some residual stress which may result in internal or surfacial cracking upon solidification, which is not desired in the cast product. Thirdly, the consideration of draft angles should be there for easy removal of the casting from the ceramic mold. Then we also need to strategically place the runners as well as the gates for optimal metal flow during pouring, because this presence of strategically placed gates and runners is essential to control the solidification of the molten material as well as to achieve the desired properties in the cast product. So step one of the investment casting route for this is basically to utilize the wax pattern generated using the following methods. So we utilize a precisely machined metal die to create the wax pattern. To create the pattern itself, we will use a metallic die, and metallic dies are quite expensive to machine. They are generally made up of tool steels, and they are, if machined properly and the die is developed in a proper way, so one die can produce several thousands of such wax patterns. The molten wax is then injected into the die under pressure to ensure accurate replication of various features. So what I mean by this is, in case there are some internal features which need to be replicated on the wax pattern, so if the wax is not injected at proper pressure, so it will not completely fill those cavities, and subsequently those shapes will not be replicated on the pattern. Pressure at which the wax is injected should be sufficient so this accurate replication of the features takes place. So wax material should also have the desired properties for easy removal from the mold. It should not be that the wax which is there, it should react with the internal surface of the mold, thereby creating the any residue on these metallic die molds. Okay. In step 2, the wax pattern assembly is then connected to this central sprue, which is also a wax bar. So wax pattern is repeated to form multiple parts. For example, in this steam turbine blades, as we know, there are several blades on a rotor disc. So it is very much desired that maybe some number of blades, 6 to 8 blades, are cast in one cycle. So these individual wax patterns of various blades are attached to the central sprues, forming a cluster. So then this sprue basically serves as a channel for the molten material to enter into the mold cavity during pouring. Strategically placed runners, they connect the sprue to each individual wax pattern, which ensure complete filling of the molten material uh, inside the wax pattern cavity, which is left behind after dewaxing. So here we can see various filled pattern waxes. There are some waxes for non-filled patterns. Runner waxes are there. Water soluble waxes are there. Sticky waxes are there. So here we can see different types of waxes which are used in the investment casting process. Step number 3 is basically building of the ceramic shell. So ceramic shells are very much desired in the investment casting process, because ceramics, as we know, they are stable at high temperature, and ceramic building of the ceramic shell is accomplished using the following steps, in which the essential step is to dip the wax cluster, which is created by assembling various wax patterns, into a refractory ceramic slurry. So refractory means the ceramic has high temperature, a high melting point. Each dip into the refractory ceramic slurry, it deposits a thin layer of ceramic material on the wax pattern as shown here. So this inside in this purple is basically the wax pattern, and this yellow color is basically the coating of the ceramic which is developed around this wax pattern. So this slurry is allowed to dry between the dips so as we are able to build a progressively thicker and stronger ceramic shell. So the thickness of this ceramic shell will be dependent on the weight of the casting and other factors, and multiple layers are applied to create robust mold capable of withstanding the weight of the molten material. Of course, there is the considerations of handling of the mold, etc. So generally few millimeters of thickness is desired, which is achieved after several dips into the ceramic slurry. Once the ceramic slurry is coated around the wax pattern, we go to the dewaxing process, which is step 4. And in this process, the wax which is present inside the coated ceramic shell is removed. To remove this wax, commonly steam autoclave and chemical leaching is applied. In the steam autoclave, the wax cluster is exposed to high pressure steam, which ensures the wax is melted away and drained away. Chemical leaching also is utilized to remove the wax, in which the wax cluster is submerged in a chemical solution that helps to dissolve the wax. But in this case, it is often reported that reusability of wax is reduced. So, in case of steam autoclave, the molten wax can be recovered and reused for making the patterns again. In step number 5, we have the metal melting and pouring. So in this step, the molten material, now in this case the molten material will consist of the nickel and chromium based alloy steels, which are the preferred choice of materials for steam turbine blades. So the metal pouring is done in the following steps. The chosen metal alloy is melted in a separate furnace and is brought above its liquidus temperature. The molten material is then carefully poured into the ceramic mold cavity, which is created by the dewaxed shell. So gravity filling or vacuum assisted methods may be used for ensuring the complete filling of the mold. So in step number 6 is the solidification and cooling. After the molten material is poured into the ceramic pattern or the ceramic mold cavity, it is allowed to solidify in the ceramic mold. The cooling rate is carefully controlled to influence the grain structure and properties of the casting. For example, in the gas turbines, we have seen the use of specialized furnaces along with the grain selector to create single crystal cast gas turbine blades. But that single crystal cast gas turbine blades were desirable for the operating conditions for the gas turbine. Nevertheless, for the steam turbine, the directionally solidified blades are also sufficient for getting the desired properties. And by controlling this cooling rate, we can do the directional solidification. And in this case, it is important to note that rate of cooling, it also influences the grain size, and to get finer grains, it is desired to cool at a faster rate, because slower cooling results into coarser grains which are not desired for enhanced mechanical properties. Step number 7, this involves breakout and cleaning. So after the solidification of the molten material is complete, the ceramic mold is broken away to reveal the casting. The process is known as shakeout. This process can also involve vibrations, mechanical hammering, or water jet cutting. So this vibration or hammering and cutting will remove the ceramic shell from the outside, and the casting is then cleaned to remove any residual ceramic material or the invested material into it. So if we see what are the specific advantages and limitations of the investment casting for the steam turbines. So in case of advantages, the investment casting is very suitable for the complex geometries with tighter tolerances. It is also very helpful to get the desired surface finish. It allows for wide range of high performance alloys like nickel chromium steels to be cast. More importantly, it also helps to create near net shape parts, minimizing machining waste. But it also has certain limitations. As the size of the turbine keeps on increasing, the capability of the investment casting process is limited by the size of the product. Higher cost compared to other casting methods is there. Surface roughness, to get very fine surface roughness, some secondary processing or finishing may be needed, and very complex features may sometimes become difficult to cast, so specialized methods may be used to manage this. So in conclusion, we can say for manufacturing of the steam turbine blade, investment casting process is a very versatile and reliable process for manufacturing complex high precision components. It enables creation of the intricate geometries with tight tolerances for essential and efficient operation of steam turbine. It also helps to cast various alloys, nickel chromium alloy steels with necessary mechanical properties, which also are able to withstand the demanding environment operating conditions. And near net shape helps to further minimize material waste and production cost in the steam turbine blades. So with this we come to the end of this lesson. Now we will summarize what things are covered. We have looked at the investment casting for steam turbine blades. We have looked at the process and methodology of investment casting. We have looked design for manufacturability, that is ease of manufacturability considerations. We have looked at all the steps in detail. Casting in detail. And lastly, we have concluded the various advantages and limitations of this process for the steam turbine. So in the next lesson, we will see the deformation processes which are used for steam turbine blades. Thank you.